What we're going to do now is the derivation of the angular frequency, and hence we'll also get an expression for the period, of a simple pendulum with a massless string of length L, a bob of mass m, that's right here, that mass m, and on a planet with acceleration due to gravity g. And this pendulum is displaced from the vertical by angle theta. So before we do this, though, we need to understand a very important concept that is essential for this derivation. And to show you this concept, what I've got right here is an Excel spreadsheet. And what I've got right here is a column with various angles. I've got those same angles but listed in radians. And then I've got their value in radians written decimally. So this is just pi over 2, this is pi over 4, pi over 6, pi over 12, etc. all the way down to pi over 180. What I'm going to do is show you the sine values of each of those. Sine of theta. So I'm just going to say equals sine, close open parentheses, of this thing right here, C2, that's the column right there. And then notice I get 1 for that. Well, that's pi over 2, no big surprise. But here's something interesting. Now I'm going to do sine of pi over 4. 0.707. Now you don't see a relationship of this, the value of theta and the sine of theta yet. Let's go down to a smaller angle, about 30 degrees or pi over 6. 0.5. Now that's kind of interesting. Pi over 6 is like 0.523. The sine of theta is 0.5. Let's see if this relationship becomes more clear as I go down to pi over 12. 0.261 is theta. 0.2, it's rounded to 0.26. Let's continue this and see what happens. Hey, now we're starting to see something. Theta in radians is 0.175. This is 0.174. I wonder if I keep going, what'll happen? 0.087 for theta, 0.087 for sine of theta, and notice that that happens at around 5 degrees. They start agreeing all the way to the thousandths place. Let's keep going. 2 degrees in radians is 0.0349, and in the sine of theta is also 0.0349. And as you can imagine, this becomes even better when we go to 1 degree. Theta is 0.01745, and the sine of theta is 0.01745. Hey, for very small angles, the sine of theta is approximately equal to theta. Keep in mind that it really only works for angles. You'll get less than 2% error if you're 15 degrees or less. Because what we're about to show is that this is the angular frequency of a simple pendulum with all this stuff for small angles only. So we can only assume this. It actually doesn't work if we go to large angles. At an angle of, so I'm just going to arbitrarily set less than 15 degrees. At 15 degrees, this, you'll get
about
1% error built into your theoretical equation. So we want to go as small as possible, 10 or 5 would be even better. So in other words, what you need to understand for this is that sine theta is approximately equal to theta for small angles. You need to know this approximation. And it comes up later, again, when we do various derivations with optics, with physical optics. So sine theta is about equal to theta for small angles, but you must measure theta in what units for this to be true. Let's go back to our spreadsheet. It's gotta be in radians. It's the only time this is true. So we're going to derive this for small angles that must be, of course, in radians. So now what we're going to do is derive the expression for the angular frequency of a pendulum. And once you do that, then you've got the period of a pendulum too, because the angular frequency is easily related to the period. So let's keep in mind what we're trying to do here is we're trying to get a relationship between the acceleration and the displacement. So we're trying to get some kind of relationship between the acceleration right here and the displacement right here, and that negative constant of proportionality, whatever that negative thing is right there, is going to be omega squared. Now, in this situation right here, we got to slightly adjust it because it's accelerating along an arc. So, and the acceleration is purely tangential. So what we want to show right here, to be specific, is that a tangential is equal to whatever negative omega squared is. We'll find that out. And this is the arc that this thing's going to travel along. So we want to show that this is negative omega squared times s, the arc length, because that's the displacement along which this pendulum moves. So as long as we can show the tangential acceleration is proportional to s, that constant of proportionality with the negative sign will be omega. So I'm just going to draw on here a couple of different things. First of all, it's going to accelerate this way, tangentially. I'm going to use red for this. So this is the instantaneous tangential acceleration, which is parallel to the arc length for that first instant there. It's always parallel to the arc length. So there's a sub t. Now, what is causing that acceleration? What is causing the restoring force for any pendulum? What's going to make it get back to equilibrium? Well, that would be the force of gravity. So let's go ahead and draw in the force of gravity right here. And let's draw that right here. Here's the force of gravity down that way, mg. So my restoring tangential force, F tangential, is equal to what? Well, here's mg. Force of gravity is right here. What is the tangential component of that? Well, mg is the hypotenuse. This is angle theta. We can get F tangential is equal to mg sine theta in magnitude, but I have to put the direction in here. It is negative because the angle theta would be positive to the right up like that, so that would be positive theta, and this is a negative force. It's in the opposite direction of the displacement, which is exactly what we want. So that's how we start. Now, what I wanted to do is get it to look more like this. How can I get F tangential to look more like this with A tangential there? What do we have to divide both sides of our equation right here by so that instead of F tangential, I get A tangential? Well, if this is the net tangential force, all I got to do is divide both sides by the mass. F tangential divided by the mass, which equals negative g sine theta. Notice that this F tangential divided by mass is just A tangential. Now we're getting really close. A tangential equals negative g sine theta. But I don't have this arc length there, S. How am I going to get the arc length here? Well, if you look at this situation and you remember our relationship between linear and rotational variables, remember that S equals r theta from rotation. But in this case, what is the r? Oh, that's just L. So we've got S equals L theta for our pendulum. So I can rewrite theta as theta equals S over L. So this is going to be key right there. This thing right there. So I'm going to go ahead and rewrite A tangential equals negative g times sine of, instead of theta, I'll put S over L. Now we're only one step away because for small angles, sine of theta is approximately equal to theta. So for S over L, for sine of S over L, I can just make that like this. A tangential equals negative g times just S over L. I'm almost there. I just need A to be proportional to S. What's the constant of proportionality? Here we go. Here's the punchline. A tangential equals, how do I get just S over here? I just want S over here. What is this thing, this negative thing, that is going to be multiplied by S? G over L. And that's where omega squared goes. Therefore, omega squared equals G over L. Like that. So we now know that the angular frequency is equal to the square root of G over L. So what this means is, if you're on a planet with a high acceleration due to gravity, you'll get a pendulum that's moving back and forth faster. If you have a very long length, the longer the length of the string, the slower it goes back and forth. So here is our result. And I will leave it to you to show that, therefore, the period of a pendulum is, since it's 2 pi over omega, that we can show that the period of a pendulum, T pendulum, is equal to 2 pi times the square root of L over G. Personally, I prefer to memorize the omega value because that's always the square root of something over something. What will make it go faster back and forth? Having a planet of higher G. What will make it go slower back and forth? Having a longer L. Now, this makes perfect conceptual sense. Notice that the mass is nowhere in there. It may be for a spring block system, but for a pendulum, why is it that the mass doesn't matter? Why is it that regardless of mass, whatever I drop, something light or something heavy, like this, these things will drop at the same rate? Why is that? Because the greater the mass, proportionally the greater the force. So the mass of a pendulum will have no effect on the period. It also is true that as long as you keep the angle small, and I arbitrarily say, well, under 15 degrees, as long as you have very, very small angles, the amplitude doesn't matter either. So there we have it. I'm also going to prove this right now for using calculus. Now, the calculus-based derivation is pretty much identical. On the AP Physics C exam, they really want you to write the acceleration as d squared s dt squared. It's the second derivative of the arc length right there is, so that is the tangential acceleration, and that'll be equal to negative g sine theta. Now I can write, notice that I can substitute for theta s over L right here. So that gives me d squared s dt squared equals negative g sine s over L. And I still have to do the same substitution for small angles. That means that d squared s dt squared equals negative g times s over L. Where you substitute for small angles, the sine of s over L is equal to the angle itself, to s over L itself. So then what I can write is just very simply, same thing, d squared s dt squared equals negative g over L times s. Whenever you see the second derivative of something being equal to some negative constant times that something, that's simple harmonic motion, and this right here is omega squared, g over L. And that's all there is to it. Now, if you are in the AP Physics C class, you definitely have to derive a similar thing for a physical pendulum. Make sure you can do that, the same derivation, but for a physical pendulum. And hint, you will have to use, or for that matter, for a torsional pendulum, instead of s, the arc length for a torsional pendulum, you're going to have to use theta. And similar derivation for a physical pendulum. So make sure you can do those as well. And talk to me if you can't, I'll show you how.